All right, welcome to Project 2, Video 2. I'm going to talk a little bit more about data structures here, but I hope just generally that Project 2 has been a really educational experience, that you've experienced the struggle of trying to plan a large project, seeing just how much complexity there is, and thinking about all the ways that you can try and manage it, because it's a lot, right? Like, just trying to keep everything straight is quite difficult. So I hope the struggle has been real and that you have liked this struggle. Because your predecessors have voted overwhelmingly, and perhaps you shall too, that there really ought to be one project in the semester that is just a brutal beast. So let's talk about data structures. Some of you guys at office hours and in discussions with TAs, it's become clear that some people are really anxious about data structures. They're not quite sure if they're doing it right, and I can understand that hesitation. So we're going to talk a little bit more about them. So in the last video, we discussed why a data structure where it's just a string isn't so great, because it's slow, because you can't insert into the middle of it quickly, because it's not easy to support clicks. And so a better solution we alluded to in the spec is having some kind of linked list of JavaFX text objects. Okay, so we did discuss how a linked list, just a plain old linked list, wouldn't necessarily be fast, or at least I posed the question here. Using a Java util linked list wouldn't necessarily be great, and that's because the add operation in a linked list, you guys know how linked lists work, right? You've written one in in linked list deck, and you know that inserting to some random position in the middle is going to be relatively slow. If I have a list of a million items and I want to insert in the middle, I'm going to have to scan my way through. So in Java util.linkList, for example, if I'm adding to position 1000, I need to scan 1000 nodes in order to insert, say, a new text node. Depending on what your add operation might look like. Okay, so maybe your add operation actually takes node objects. I don't know, whatever. And that's just, again, because the util linked list that is provided by Java, it has to go all the way through. So the normal way, and the way all of us who did the project did it, was to build our own fast linked list that keeps track of the current position. So what does that mean? Well, unlike a normal doubly linked list where you might keep a front and a back pointer, instead we keep a current position pointer. And then if I want to add a character, well, I'll insert it here in between C and D. And if I have a backspace, well, I'll remove this node, and that should be relatively quick. Okay. Now this isn't the whole thing. I'm not showing the sentinel nodes, but I'm omitting it just for graphical simplicity. Okay. So here's another example of I'll call it a fast linked list. So a fast linked list based approach. So in this approach, our editor class has a fast linked list object. And what is a fast linked list? Well, it has a sentinel node that was not depicted on the previous slide. It has a current position integer, which may or may not actually be useful, but I put it here because it seems like it might be useful for, I don't know, printing, debugging, who knows. We have here a current node, which is our pointer to wherever we currently are. And this is the big difference here, is the buttons that are available to you whenever you have one of these things in your hand. The fast linked list is a different abstract data type than our normal linked list. Normal linked list, you can add to the edges, you can add to the middle, whatever, but our very simple linked list that we're building has just two operations, the one I have in mind. You have one that's add character. So in this case, if you have a particular character in mind, it will add the given character to the linked list after the current node. So it'll create a text node or whatever node, a node object, and it will add that. And when you delete, well, it'll delete the current node. And then current position might be useful for other reasons. Now, what is a node? Well, a node contains a text object and then a previous and an next pointer. So if we imagine that we have that data structure, let's think about what this does for us compared to the string. So when it comes to insertion and deletion, I hope it should be clear that this is going to be really fast. Since we have a pointer to the current node, and our two operations are add character and delete character as defined here. This is our semantic specification, as we put it in that last lecture before we did asymptotics 16. These operations, we can support them in constant time. It's just going to be quick. Now that's not counting the time we might need to update all the x and the y coordinates, the text object, and all of the cascading changes for line wrapping, and that's fine. Because this stuff, changing the x and y coordinates of the text objects, that's going to be the rendering step, the drawing step. So we don't count that, okay? This is fine because this is part of rendering. Okay, and rendering just means drawing, if you haven't picked that up earlier. Hopefully you did, okay? How about arrow keys, right? So imagine again, the only thing we have is the ability to, we have just this thing. So if we have up or down arrows, though, so if we're changing the cursor position with arrow keys, if we press the down arrow, well, when we press down, we can scan forwards using Java FX methods to keep checking the width of each character as we go until we finally hit the same character again, kind of like what we did with the string example in the previous video. Not that my explanation for that was amazing, but I don't want to give away everything. But the resulting runtime in that case is going to be constant, right? So again, I mean, I guess the simple part is just if I push down, and you imagine this whole piece of text here is stored as a linked list, when I push down, I can scan forwards each character, checking widths of characters until, checking the widths of characters. When we get to the next line, right, when we go from here to here, then we'll set the position of the cursor as appropriate. So this thing's going to scan its way through. And that's actually a constant time operation. And the argument is simply that the window is only this wide. It does not matter how long the file is. It could be the entire text of Moby Dick. The width of the page isn't going to depend on that, right? So the resulting runtime is constant. Okay, how about clicking? So we're going to run into a problem here that I referred to at the end of the lab, right? So if I'm trying to change the cursor position with clicks, like I click here versus here, it is not good to scan all the way through the file until you finally find that position, because the user might, for example, scroll up, click here, scroll down, click here, and that means it's going to be, at worst case, linear in the length of the file. So that means our data structure, there's just no way around it with the data structure we have. We have a long stream of characters. So naturally, if I want to get the position from, say, B all the way to the last character, maybe a million characters later, it's going to be linear time. Okay? And then rendering we're not going to talk about in this video because it's not really pertinent. Okay. So the issue then becomes, if we're using a linked list, how can we fix it? Okay? So the fundamental problem is just that we cannot handle clicks in constant time with what we have. So there's two common approaches that I've seen in office hours that I think are reasonable. There are others, I mean, this isn't exhaustive, I'm sure. But it seems to me that there's two basic themes that occur. And one of them is augmentation, which is to store the information you need for constant time click in a separate data structure. And the alternate approach is what I'm going to call the fission approach, where instead of keeping one giant list of the whole file, you keep a bunch of different lists, one for each line. Now, based on discussions that we've had among the TAs and myself, we're pretty sure, but not 100% because we all did the augmentation approach, but we're pretty sure that the augmentation approach is going to be less work. And I think that, well, we'll see some examples later of why the fission approach, where we split things. Fission, of course, just means splitting, right? If you know nuclear fission or biological fission. But basically, we'll see why the fission approach, if you have to split the lines into separate lists, why it might be a little slower. Okay, so let's compare those two approaches graphically. In the augmentation approach, you have all of the characters in the entire file in one big old list. Let's say this is the screen. It has A, B, C, D, and it's such a tiny window that it actually wraps. So we have A, B, C, D, and then I have a second data structure that's going to keep track of information that's useful for supporting fast clicking. Okay. And we'll talk about what that might be in a moment. And then in the fission approach, in order to support fast clicking, what you do is you have two entirely separate lists. And this also happens to make it very, there's an easy correspondence between this and the rendering, right? So that also makes it seem kind of appealing. But in this case, we have two lists, one that's AB, one that's CD, okay? So I hope that makes some sense. We could either keep all the characters in one big old list, or we can keep it in separate lists. And we think that this version is going to be easier, and this right here is going to be just some extra information you need to make the operation of clicking faster. Okay. So what might this thing be? What is this data structure that could be fast? Well, I'm not going to spoil it here in this video, but I am going to make you think about this question. Imagine you wanted to support the operation go to line number X. Imagine that you add a feature to your text editor that you can push a button and then type a line number and it goes to that line. What data structure would you need in order to make that work? Okay, and once you come up with an idea, there's like a pretty simple idea once you understand the question and think about it, but there's a pretty good data structure for supporting go to line number X, and you might consider how would that same data structure be useful for clicks. Okay, so that's the augmentation approach. Now, since the fission approach is appealing, let's discuss some of the pitfalls that you might run into. Okay, so suppose we have the editor window as shown, A, B, C, D space E, F, right? Where the cursor is between B and C. So in the fission approach, we have two different lists. One that has A, B, C, because that's the first line, and then the other that's D space E, F. Okay? So this right here, this data structure represents this window buffer. And if we press space, of course, what will happen is this is going to push CD to the next line, and then there's not enough room here, so EF gets pushed to the next line. So in a fission-based approach, when you press space, changes can cascade, right? So you need to move things between different lists, okay? And that doesn't happen in the augmentation approach, because this data structure, you'd just be adding a space in the middle, and you'll be updating whatever this thing is. But in the fission-based approach, you're going to have this cascading changes all the way down. So in a the fission-based approach, we can imagine that the updating process looks something like this, right? So when you press space, you could, at this point, when you press space, you will temporarily have A, B, space, C, D, space, E, F, right? That's the insertion operation, that's constant. And then maybe during your rendering phase, what you'll do is you'll do all the cascading changes so that everything right here matches or can be displayed easily. So in the rendering phase, you would kick the C down to the next list, and that would maybe send also this EF to the next list. Okay. So that's what the fission approach looks like. That's what I mean by cascades. Whenever you kick C to the next list, it also causes E to get bumped to the next list, okay? Or EF gets bumped to the next list. So you have our blessing to do a two-stage fission update, right? So the runtime might seem a little wonky, right? Like, wasn't I supposed to insert in constant time? Isn't this not quite an insert? Isn't this really what an insert is? There's some philosophical questions that have come up at office hours. But basically, you have our blessing to do this. So if you're a little bit in doubt about whether or not your insertion operation is okay, be aware that we've considered this and decided that this counts, right? That this is we'll count this as constant time insert, okay? Even though one might argue it's questionably linear, but I want to open up the possibility. However, we think it's going to be more work to do this approach due to cascades, especially given the example on the next slide. Now, if you decide to do what I'll call the fission approach, maybe this two-stage fission or something similar, I want you to make sure your code does not take quadratic time to open a file, because that will be a ding, right? Now again, right, the project is 40 points. Some fraction of those points is going to be for run times, but not all of it. So if it comes between, your health or getting any work done and however many points quadratic time is, and we haven't decided, but if I had to ballpark it, maybe 10-ish points will be all of the timing. I don't know, maybe slightly less. Then by all means, maybe don't spend all of your next however many hours being super stressed out, because you can always make a quadratic time approach, get it working, and then later refactor your code. Okay. So one issue that popped up at office hours that I think makes the augmentation approach especially potentially tricky, it's a little harder than it might seem at first, is the following case. So let's suppose we have, hello, cows say moo, okay, and I think they are cool. So if you press space right here, well, in that case, you've made mo short. So mo can actually get kicked to the line above. So in other words, the naive approach is that when you press a key, if you don't count space, the only thing you're ever going to do is cause down propagation, but actually you can also cause an up propagation. And so that means that you need to think really carefully. If you have a fission-based approach, then it is possible that sometimes you're going to have to actually move things up a list. Okay. So for that reason, just think real carefully about the fission approach before you decide to really truly go with it. And if you can avoid that issue of this cascading with the augmentation approach. You'll still need to update this mystery data structure, this thing here, but we think it'll be less work than trying to deal with this cascading issue. But again, Project 2, this is your opportunity, your one opportunity in 61B to really do more or less whatever you want. So we don't want to restrict you too much, okay? So some just closing words here in this video. These are the frequently asked questions, things that have come up on Piazza, 3 times a day, or in office hours repeatedly. Also some warnings and just a couple of recommendations, okay? So we recommend that when you create a data structure, you store text objects, not characters or strings. Now you can do it with characters or strings, but if you've started hitting some roadblocks, then maybe it's time to switch over to text, and you might find it's a little easier. Another important point, it's possible to take an existing text object, like say you have the letter A here and you want to move it up. You can actually change its X and Y coordinate using setX. You don't need to destroy all your text objects and recreate them. You can just say, okay, well, we have a bunch of texts. We can move them using set X and set Y. Another is when you're drawing to the screen. We have that get children method. You don't need to remove all of your children and draw them and add them back every time you draw to the screen. That's unnecessary. Okay? It is okay, and I alluded to this earlier in this video, but it's okay whenever you push the up or down arrows to scan from one line to the next, because each line is constant in length. Okay? So a lot of people have been worried about that, but that's actually totally above board. And then as far as timing tests goes, I just want to give you a little picture of what those might look like. Well, one of them is going to be, we click at the beginning of the file, the end of the file, and switch between the two, and ensure that the runtime is constant for doing that, right? So that should not be linear. Another we'll definitely have for you is, well, we probably won't provide these client side, but we'll run them when we have the graders, is we'll open a large file and ensure that opening takes linear time, not quadratic time, because that would mean that opening a big file will take forever. Okay? Now, we will not be directly testing constant insertion time, right? Because we have no way of isolating this part of your code. However, I want to note that opening a large file must still be, I almost got through the whole thing without a bug. Error. Must still be linear time, okay? So this right here, just to reiterate my point, what I'm saying here, whenever you insert, right, we have no way, because of the way the program works, we can't isolate this step. We can't prove that you're using a fast linked list versus a regular linked list. However, it's really not that hard to go from linked list to fast linked list. And I think it's a great exercise to keep things fast. But in the interest of total honesty, I will say that constant insertion time, there's just no feasible way, given the fact that it's an API-free assignment, for us to test it. Okay. And then lastly, another note that was that has come up in office hours, inserting into the middle of an array list is linear time. And you should know that. I mean, maybe not like a fact that you know, like breathing oxygen keeps you alive, but somewhere buried in your knowledge is this knowledge, because you built an array list. You built an array deck in Project 1A, and as you know, inserting in the middle of that list would have to be linear time. There's not really a way around it. Okay. And a quick reminder on the project late policy. So the project is due Monday the 7th at 11:59 p.m., but there's a little bit of a grace period. So the first day you can only lose up to 2%, right? So if you wait another 24 hours, it's 2%. But then after that, at 10% each day, which is, if you get a perfect score on the project, 4 points. So fairly friendly compared to, say, 61A. And there's also this basics autograder, which is due on the 2nd, which is Wednesday. And that'll be at 11:59 p.m. So originally, of course, it was due March 1st, and it was supposed to be out the day before, but we just pushed both those deadlines out. And so, you know, we've had various very interesting technical issues for building this one. And so Ross, who has been piloting this backup plan, tells me that the client-side autograder will be available late tonight. It's already pretty late, so, you know, hey, seems fine. But this is not an autograder that is going to teach you a lot, because it's not like Project 1, which is a huge suite. This is just a few basic sanity checks. So I don't think anybody's suffering too much for this autograder. It is exceedingly unlikely that we will change this deadline, because this is not a software engineering course. And if it turns out that our project's too big, we'll just shrink the project a little. So what I mean by that, in the course policy, as we said, we reserve the right to take normal points and move them to gold points. And in that way, if you've already done the later parts of the project, you'll still get rewarded, but it'll just be gold points, not something we expect everyone to do. Now, we think we got it right, but, you know, we'll keep our ear to the ground, and we'll be listening carefully to make sure not too many people are hurting too much. But I'll note that compared to last semester, or last spring, when we had Gitlit, well, this project's smaller than Gitlit, and we also didn't have a midterm in the middle of working on it. So I think things are fine. But, you know, maybe we'll trim some of the later features, but don't count on it. That said, you know, I do know this semester I've been really bad about slipping deadlines by a day or so. But I've been early, too. You know, sometimes I put things out a day early. So don't forget that. But, yeah, it has been the craziest semester of my life. So I apologize for the occasional slips. I know it is lame, but hey, doing my best. So I hope you will forgive me. So, yes. Anyway, that's basically Project 2. Again, I hope you're really enjoying it. And I know it's hard and I know it's stressful, but yeah, you know, blame everybody the previous semesters who said they love all these super hard projects. That's basically it. Though I will note there are some extra slides, by the way, if you want to check them out online. I'm not going to talk about them right now, But yeah, best of luck, and I will see you soon.